Hi, this is for homework 10 and this is question 1. First, we want to collect the definition and some simple property of stochastic processes. First is Poisson process. Poisson process in the first property is that the number n, t1, t2 of the point ti in the interval t1 and t2 of length t equals t2 minus t1 is a Poisson random variable with priority lambda t, and this is the function. 2. If the interval t1, t2, and t3, t4, they are not overlapping, so the random variable n, t1, t2, and n, t3, t4 are independent. And 3. At a time moment t, there is no more than one point, a Poisson point. Using the point ti, we form that stochastic process xt equals n0t. And for Poisson process, the first order probability method is this. The mean should be lambda t, and the autocorrelation rt1 t2 equals lambda squared t1 t2 plus lambda times the minimum of t1 or t2, and the autocovariance c t1 t2 equals the lambda times minimum of t1 and t2. So the mean of Poisson process is lambda t. So lambda t is a linear function of t. So we can say that if we wait for longer time, the expectation number is larger, right? Because it is a linear function. The autocorrelation function contains the minimum of t1 or t2. So this is come from the property of independent increments. And the second is Poisson increment process. It is defined like this. And here xt is Poisson process. For this, the first order probability method is this one, and its mean is lambda. The autocorrelation r is lambda squared if t1 minus t2, the absolute value of t1 minus t2 is greater or equals to epsilon, or this if it's less than epsilon, and this is the autocovariance. The Poisson increment process is you can see the autocorrelation here, this term. This is a triangle with area lambda, which is independent of epsilon. So when epsilon goes to 0, the triangle becomes an impulse with area lambda. And this is very similar to this process, the Poisson impulse process. This is the definition, and we don't have a method for its probability methods. The mean is lambda, and the autocorrelation is lambda squared plus lambda to delta t1 minus t2. The autocovariance is lambda delta t1 minus t2. So the process zt minus lambda, this is because the mean of zt is lambda, so zt minus lambda, this mean should be 0, right? And rt1r should be lambda delta t1 minus t2, and the zt minus lambda is a white noise. And for semi-random telegram graph signal, the number, let's say, this is Poisson random variable, so this should be the semi-random telegraph signal. It's for its first order probability methods is like this one, and its mean is e to the power of minus 2 lambda t. Its autocorrelation is e to the power of minus 2 lambda times the absolute value of t1 minus t2, and its autocovariance is e to the power of minus 2 lambda times the absolute value of t1 minus t2 minus e to the power of minus 2 lambda times t1 plus t2. So the probability of xt equals 1 is not 1 seconds because we start with plus 1. It should be a little higher than 1/2. The probability of this goes to 1/2 when t goes to infinity, which, yeah. And this goes to 0 when t goes to infinity, right? And this goes to 0 when t1 minus t2 goes to 0. Oh, goes to infinity, sorry. And for random telegraph signal, here we have yt equals axt. And the probability of a equals 1 and the probability of a equals minus 1 is 1 second. And here the xt is semi-random telegraph signal. First is first order probability method is like this, and its mean is 0. Its autocorrelation is e to the power of minus 2 lambda times the absolute value of t1 minus t2, and its autocovariance is the same. So as you can see here, both these probabilities are 1/2. This makes us think that a yt maybe is strict sense stationary. And as you can see, its mean is 0. 0 is constant, so we can guess it's an SSS. And for random walk, it's like you toss of fair coins and time, and k is the number of the heads, so the number of a tail should be n minus k, and this is random walk. Its first order probability is this, and its mean is 0. Its autocorrelation is minimum of n and or m times s squared. So does autocovariance. So from its probability methods, we can say that when n goes to infinity, we have the Gaussian density, right? And for linear process, here xt is random walk. Its first order probability is method is like this, and this means 0, 2. and these are autocorrelation and autocovariance. So Wiener process has some property like W0 equals 0 with probability 1, and W has independent increments like WT plus U minus WT is independent of sigma, and so on. That's for question 1.